Welcome to NPTEL online course on fractals and multifractals. So, in the second part we have discussed the dimension theory. In the last lecture we have defined what is multifractal, how it differ from the usual fractal measures, that means the Hausdorff dimension and fractal dimension. What is the drawback of Hausdorff dimension and fractal dimension? Fractal dimension and Hausdorff dimension both measures the how the number of boxes grow whenever the scaling size is tends to 0, but it does not give what is the inside boxes, whereas in the multifractal gives the detailed version of the fractals as it counts the measure inside the boxes. Now, in this lecture we are going to discuss some fine examples where the fractal and multifractal is distinguished by mean of its measures. That means how the fractal is classified in terms of multifractals measures. So, let me recall what is the multifractal measures. For defining the multifractal measure, first we need to define what is the Holder exponent. The Holder exponent here we defined as ln of mu of box over ln of delta. For example, if we have the structure like this one, we need to find the partition of this object by giving the cover of the object. For that, maybe we are taking the equal covering, but each box has the same length or same size. That means each box of this size we can call it as delta. Now, one can understand that this number of boxes required to cover this object and this delta follows the power law property. That means n of delta is directly proportional to delta power minus df, where this df we are calculating for the box counting dimension or fractal dimension, with limit delta tends to 0, then ln of n of delta over this ln of minus delta we are calling as the box counting dimension or fractal dimension, that we may denote as dB. So, here now if we have the delta, this delta divides this object. If you are having the delta size boxes, this delta size boxes divide this object. So, it forms the cover of an set S, we can call it as maybe the set capital S. Fine. Now, here we simply count the n of delta denote the simply the number of boxes is required to cover this object. More precisely, the minimum number of boxes, whenever we are taking the minimum, then it will give the exact cover of the set. By taking this minimum, one can get the box counting dimension. So, here we simply covering the number of boxes. Now, instead of counting the number of boxes, now we are defining the measure on each boxes having the size delta. That means this, for here if we have these boxes, for each boxes we are giving the measure, that is I can call it as mu of box, that means the density of the boxes we can call, that is we are denoting as the measure of the box. One can understand this is the regular curve, Suppose we have the curve like this one, more like this one, like this kind of curve. If you cover the same size boxes, maybe I will choose a different color to distinguish this. If you are using the same size like this one, size of boxes is same, the length of each, that means here it is a length I am covering because I am taking the curve, so length is same. Now one can understand from this both the figure. So here delta, this curve is like a smooth curve. Here the term is somehow fluctuation compared with this one, it has more fluctuation. If you are using this box counting dimension, again it will cover the number of boxes. Again it will cover the number of boxes. Here also it will cover number of boxes. Suppose you can assume that this object and this object have the same number of boxes is required to cover the object, then their both the fractal dimension or box counting dimension will be same. Now we introduce the measure mu on each boxes. Here each box size is delta. So one can understand that with respect to delta, this mu is not equal because measure of the box it vary with respect to the object. Here the object has more fluctuation. So the measure of box, the measure of the box is vary. For example, here and here you can take the measure of, if this is the box 1, if this is the box 2, then the measure of box 1 is not equal to measure of box 2. So here and here it has two different measures. So this measure, that means now we are looking what is inside the boxes. Simply instead of counting the boxes, we are now looking what is inside the boxes. Now this number of boxes, that means the measure of boxes, and this delta, that means the box size, follows this power law property delta power alpha. Now this mu of box is directionally proportional to delta power alpha. Then here one can obtain as alpha equal to, we will get the logarithmic constant. Whenever this delta tends to 0, that our logarithmic constant will ignorable. So we can get ln of measure of the boxes over ln of this delta, size of the boxes. Here it follows this power law property with respect to this scaling. This scaling now we can define as the Holder exponent. So with respect to delta, the number of delta and this delta have the inverse relations. Whenever this delta is decreasing, the number of boxes will get increase. The number of boxes required to cover this object will increase. Similarly, this object will increase. So whenever we are getting this delta close to 0, we will get the finite covering. So we will get the finite approximation. So this alpha now we are calling as the Holder exponent. Now you can understand, whenever this alpha value is lesser value, the alpha is lesser value, then the measure, that means the alpha is lesser in this relation. If alpha is lesser value, that measure of the boxes is high density. It has the object has the high density, that means the higher measure. When alpha is larger value, because this delta tends to 0, if alpha is larger value, this measure will get decrease. The measure will get decreased. That means this controls, this alpha controls the measure of the boxes. Therefore this alpha is called the singularity exponent of the measure mu. we can call this alpha as the also singularity exponent of the measure mu of these boxes. Now, after defining the Holder exponent for this object with respect to the delta, now one can count the number of boxes of size delta having a Holder exponent alpha. Since you can see here in this figure, here maybe the Holder exponent for the all the boxes it may be equal because the curve is like a smooth curve. Whereas here if you are consider, if you are finding the measure of these boxes and these boxes is not same. Maybe you can assume that here this is 1, here the 1 boxes and 2 boxes and 3 boxes. Assume that the 3 boxes have the same measure. And also here 1 dash, 2 dash, 3 dash. You can consider here the curve is like a linear curve. So here the measure are equal. Now with respect to the delta size, here the measure of these boxes, is same. Therefore 3 boxes having the Holder exponent alpha because we are fixing some alpha. The alpha we are fixing the range usually we are fixed and check this is equal. And similarly here there are 3 boxes having the same Holder exponent. Now n delta of alpha of, that means n delta of alpha denote the number of boxes of size delta having the Holder exponent equal to alpha. Now by varying this alpha, usually the alpha varies from minus infinity to plus infinity, whereas we are taking some in the closed interval. We can take in the range from the closed interval in the this satisfying the scale property, we can take in the closed interval. The alpha value lies between these two domain minus infinity to, maybe we can take 0 to infinity or minus infinity, but we are taking in this domain any closed interval. By varying this alpha, likewise we can cover this delta of boxes and we can count number of boxes of size delta having a Holder exponent equal to the alpha. Now we are defining what is f of alpha. See here the definition of f of alpha means that for each alpha n of this, the number of boxes increases when delta is increases. It has the scaling property. This f of alpha is defined as a number of boxes of size delta having the Holder exponent alpha is directional proportional to delta of power minus f of alpha. Then again here one can calculate by applying the ln of n delta of alpha equals some the logarithmic constant ln of c time delta power f of alpha. This can be written as ln if you are calculating f of alpha here, then f of alpha one can get minus delta, that means ln of n delta of alpha over minus ln of delta. Then if you take this one, this will becomes minus ln c by ln delta. When this delta approaches to 0, this we can ignore, like a box counting method, we can ignore this quantity, then we remains with this quantity. This quantity we are writing here f of alpha as ln n delta of alpha over minus ln delta. This f of alpha and this n delta of alpha follows the power law property with respect to the scaling delta. Now we got f of alpha from this power law property. Now what is the meaning of this f of alpha? The value of f of alpha can be interpreted as the dimension of the subsets of boxes of size delta, because alpha denotes the number of boxes having the Holder exponent alpha. So here the number of boxes having the Holder exponent alpha. This is the power law property with this one. Therefore, the f of alpha denote the dimension of the subset of boxes, not all the boxes. If you are covering by the set of boxes, among all the boxes only here among all only 3 boxes having the Holder exponent some fixed value alpha 1, maybe these 3 are the alpha 2, alpha 1. This alpha 1 with respect to this alpha 1, this follows the power law property. Therefore, this only if you are consider if it is alpha 1, then n delta of alpha 1 directional proportional to delta, here delta is fixed, then minus f of alpha. So here we getting the number of boxes 3. So these 3 boxes has the fractal dimension. That means if you are fixing the delta, we can cover this object by the collection of sets. Among all the set, there are particular subset among all the collection having the fractal dimension f of alpha. So this f of alpha interpreted as the fractal dimension of the subset of boxes of size delta having the Holder exponent alpha in the limit as delta tends to 0, because whenever we are approaching we will get the finer and finer approximation. One can observe as delta tends to 0, there is a increasing multitude, maybe infinite, of subsets, each characterized by its own alpha and a corresponding fractal dimension f of alpha. Right? Whenever this delta tends to 0, then it will comes to closer and closer. Then obviously delta tends to 0, the number of cover will increase, So in that case, the increasing multitude of subsets of this, the subset from this collection, each characterized by its own alpha, because each box we are going to define the measure, based on the measure we are going to define what is the alpha exponent. We are going to collect those boxes as the alpha exponent, we are going to separate. So the increasing multitude of subset, each characterized by its own alpha, and this alpha correspond to f of alpha. That means the alpha and corresponding fractal dimension f of alpha. Then you can observe that from this figure, if delta tends to 0, you can get among all the collection, we are getting the subsets of boxes having the Holder exponent alpha, which has the fractal dimension something. Therefore, if you are considering the different collection, it has different fractal dimension. So here we are not changing the set. Our set is whether this one or like this type of structure, whether it is smooth one or like this type of irregular things. We are not changing the object. Our object is fixed. Our set S is fixed set, whether this one or this one. Now delta tends to 0, the covering will increase. Now in the covering, some sets, for example, the arbitrary, not some sets, among all the collection, we are going to take the subsets of sets with respect to the alpha, then their corresponding fractal dimension. So you can observe that in the object is same, we are covering by the boxes. In the covering collection, some sub collection has the fractal dimension f of alpha, other sub collection has the fractal dimension f of alpha. Say for here we are defining this as box 1 and box 2. That means box has the collection this one with respect to the alpha 1, then it has the fractal dimension f of alpha 1. That means also if you are taking this one, it has the fractal dimension f of alpha 2. So among this collection, this sub collection, the beta B1 collection has a fractal dimension f of alpha 1, and this B2 collection has the fractal dimension f of alpha 2. So each collection is characterized by its alpha and corresponding fractal dimension. This is one of the several reasons for the term multifractal. So here multifractal doesn't means that it is an object. It doesn't mean that the multifractal is a different object. The multifractal is a measure which classifies the object in detail by its collection and its associated fractal dimension. So, here whenever this alpha tends to 0, there is an increasing multitude of subset, each characterized by alpha, and corresponding fractal dimension we are denoting as f of alpha. So, if this alpha is range over from this closed interval, then we can get the spectrum of f of alpha. There are multiple dimension, fractal dimension. Therefore, it is called the multifractal. Multifractal, because in the fractal itself, because obviously the fractal satisfying the scale property, that means the self-similar property. If you are taking any corner of the fractal, you will get the same structure. So, if you are simply counting the boxes, it doesn't give the what is inside the boxes. Now, we define the measure that are density of the each boxes, then we are giving according to the density we are giving the dimension. So, one collection has some density, its dimension is different. So, another collection has other density, dimension is different. So, if this density is varying over from some region, then for each region we will get the spectrum of dimension. We get that is called the multifractal spectrum. If one can plot this alpha and f of alpha, they will get the spectrum like this concave curve that we discussed yesterday. So, now this is the general version of the Hausdorff dimension, and this multifractal gives the more detail than the Hausdorff dimension as well as the fractal dimension, the box counting method. Now, then we discussed with respect to this alpha and f of alpha. Say for example, the multifractality procedure we have come across in the last lecture. Let S be a set, non-empty set. S can be divided into boxes labeled by an index I. We are dividing the S as a number of boxes, and each boxes we are labeled by the index I, such that the ith boxes will have ni number of points. That means we can call it the density of the ith boxes divided by total density of the object. Of the ni points of the total n points of the set. That means if you are taking the mu I, if you are taking the ith box, the measure is defined as ni by n. If mu is the total measure of the object, then for each covering we are taking the measure as ni by n. Density of the boxes or measure of the box divided by the total measure. Then this mu I we can call it as the mass or the probability mu I. So that the total mass we can get as mu. Total mass we can get as mu. Then the MD of SQ of delta, like the Hausdorff dimension, is summation of I equal to 1 to n mu I power q delta power d, which is equal to number of boxes having the Holder exponent q comma delta is defined as delta power d. You can take this product of this term, then we will get this one. So, this have some exponent where this measure falls from infinity to 0. That critical point we can call it as the mass exponent. This exponent, the q, is raised among the masses. So, it is like a moments. We raise the power of mu I because we are calling this, maybe mu I we are calling as the probability. We are raising the power q. So, this q this exponent has some critical point. That critical point we are calling as the tau q, is a mass exponent. This tau q we are calling as the mass exponent. The tau q for the set depends on the moment of the order q. For different q, this tau q will vary. For different q, this tau q is vary. One can check this tau q will get the decreasing function of q. We yesterday proved that this tau q is decreasing function of q. Now this one, this z of q comma delta, we can call it the partition function. That means mu I of power q. That means if you are taking the sum, we can get the total mass of with respect to the moment q. Total mass with respect to the moment q, that we can call it the partition function. This partition function has the power law property. This z of q comma delta is directionally proportional to delta power minus tau q. So from here one can find the tau q. So tau q is like the box counting technique method, minus limit delta tends to 0 ln of z of q comma delta by ln delta. Then from here one can observe that delta of q is here md of s comma q comma delta is written as n of q comma delta, that means z of q comma delta. Actually the z of q comma delta, not yes, z of q comma delta. Now this z of q comma delta is delta power d. If this one associated with this number, then we can write this one as delta power minus tau q into delta power d. So here you can get delta is the power of d minus tau q. Now this d has some special quality. That means if you are taking a set S in the space D, that D represent the embedded space dimension. This D denote that embedded space dimension. This D is always greater than the tau of q. Otherwise, we will discuss while giving some suitable example that D is always greater than the tau q. Otherwise, we can get some smooth structure only. The weighted measure is characterized by the whole exponent tau q. Based on tau q, this measure md is, we are characterizing the md based on this tau q. That controls how the movement, this tau q is, the tau q is based on this the partition function. This tau q is related with this moment. So tau q that control how the moment of the probability mu I scale with the delta. So for each boxes we are defining the measure mu I and taking the moment q. With respect to the q, we are defining tau q has this relation. So here this total measure now depends on the tau q. This controls this md. That means based on this tau q, we can classify this measure md. In the some critical point, we will get the finite number. Whereas if you are taking any d value is greater than tau q, it is 0. That any d less than this tau q, it is infinity. Like a Hausdorff dimension, we will get the figure like this one. We will get the figure like this. If this assume this is infinity, then there is a critical point here. Then here in the tau q, the tau q where this infinity to 0 it will come. This is the md. So this tau q controls the measure d. This tau q that control the moment of the probability mu I scale with the delta. So here measure plays the role, whereas in the Hausdorff dimension we are not considering the measure, only considering the number of boxes. Now let us try to explain the multifractal nature, how it differ from the usual fractal dimension and Hausdorff dimension, and how to obtain the multifractal measure for the some object. Maybe we can start with our classical example, Cantor set, one chord curve, one Sierpinski triangle, and we'll check some random fractals, and thereby we can construct the multifractal formality. So, from here one can understand that if my object has this smooth nature, this alpha is same for all the boxes. Alpha is same for that means the measure is same for all the object, then I will get only one single alpha value. Whereas here I will get the different measure for each boxes, so this alpha also will vary. That we will discuss now. Now in that we can consider the triadic Cantor set. We will check is there any conservative quantity in the triadic Cantor set. So just I recall how we constructed the triadic Cantor set. The triadic Cantor set is simply the Cantor set in the closed interval 0, 1. That means we can take the closed interval 0, 1. And we can divide this as 3 equal parts and remove the mid parts, and we can make this as a 2 parts. One we will get like this one, 0, 1 by 3, and 2 by 3, 2, 1. Again divide this one as 3 equal parts, we will get 0, 2, 1 by 9, and here 2 by 9, 1 by 3, and here 2 by 3, here it will divide as 2 equal parts, then we will get this one as 1, this is 8 by 9, this is 7 by 9. So this type of structure will get after removing this one. We know in each iteration it produced 2 interval of the size 3 power 2. Here 4 interval of size 1 by 3 power, here 1 by 3 after first iteration, here 3 power 2, that means 2 power 2 interval of size 1 by 3 power 2. Hence after the nth iteration one will get 2 power n interval of size 1 by 3 power n. Now in an attempt to see if there is any conservative quantity, in each iteration we are removing one closed open interval, here removing the open interval of length 1 by 3. Here we are removing, in the first step we are removing one interval of length 1 by 3. Then here we are removing 2 interval of length 1 by 3 power 2. Here 4 interval of length 1 by 3 power 3, and it goes on. In general, in the nth iteration, n interval of length 1 by 2 interval, then if you are going to 3 interval of length 1 by 3 power 3, 2 power 2 interval of 1 by 3 power 3. So in general 2 power n interval of length 3 power n plus 1, and it goes on. We are removing this type of interval. Now we label all the remaining n intervals 2 power n as I equal to 1 to n. So in each iteration we assume that there are n number of intervals. That means in the nth interval we have 2 power n interval. So each interval we can giving the label 1 to up to n. Here n is 2 power n. And we know that in each interval the size of each interval is 1 by 3 power n, whose size we assume for convenience to be x1, x2, xn. We can assume the size of each interval as, that means we have the n number of interval, each has size x1, x2 up to xn. We know that what is the size of each interval, it is 1 by 3 power n. We know the size is 1 by 3 power n. Now we define the qth moment of the interval, size mq as the qth moment we are defining like here, mq, that means qth moment of the size of the interval is defined as xi power q, where I equal to 1 to n. Now, if you are taking m zeroth moment, what we will get? Summation I equal to 1 to n is 2 power n. Each xi has the length 3 power n. So, we can take this as 3 power minus n. Power, the qth moment is 0. So, one can get it is 2 power n. So, the 0th moment is 2 power n is the number of interval which clearly is an increasing quantity with n. Whenever this n tends to infinity, that means the iteration tends to infinity, this 2 power n converges to infinity. You can note we are taking q as 0, then this m naught tends to 0 as n tends to infinity. Now, we will find the m1, that means the total mass, sum of all the things. m1 we are defined as sum of I equal to 1 to 2 power n, here 3 power minus n power 1, because the first moment we are finding. So, which is equal to sum of 1 by 3 power n up to 2 power n times. Therefore, it is 2 power n times 3 power minus n. 3 power minus n. But you can consider the 2 power n. The 2 power n is as per the number of delta, that is n of delta is directional proportional to delta power minus df. Now, this 2 power n, the 2 power n is directionally proportional to the 2 power n number of interval, each of its size is 1 by 3 power n. So, 3 power minus n df. If you replace here, then one can get 3 power minus n df, 3 power delta power minus df. Yeah, there is okay, here 1 minute. Here 2 power n is 1 by 3 power n minus df. So, which is equal to 3 power n df. 3 power n df. So, here it must be plus, then here you will get minus n. So, which is equal to, if you are taking 3 power ns out, then one can get, if you are df minus 1. So, this can conveniently write 3 power minus 1 minus n times 1 minus df, because this Cantor set embedding in the closed interval 0, 1, therefore, we are writing 1 minus d power n. Now, you can observe this quantity 1 over 3 power n 1 minus df. Now, whenever this n is increasing, then m1 is a decreasing quantity. That means, if you are taking q equal to 1, then the first moment is, that means the total mass is 10 to here m naught tends to infinity. Yes, because q equal to 0, 2 power n we are getting. If n tends to infinity, m naught tends to infinity. Here q equal to 1, then m1 tends to 0, because it is a decreasing quantity. This is our m1. Whenever n tends to infinity, this m1 tends to 0. This m1 is a decreasing quantity with the iteration, because if you are going with the iteration, this is a decreasing quantity. So, there is a intuition say there must be a value of q between 0 and 1. There must be a value between 0 and 1 for which the moment will remain constant. Here, with respect to the iteration, the 0th moment tends to infinity. Here, with respect to the first moment, if iteration tends to infinity, the moment tends to 0. Now there exists a quantity, that means the exponent q between 0 and 1 such that there its moment will be remain constant. That means that moment will calculate now that md, maybe I will use here. So there exists a q between 0 and 1 mdf. If you are applying this moment, then means summation I equal to 1 to 2 power n, because our size of the interval 2 power n, xi, that means the size of the mass of the each interval is 1 by 3 power n df, which is equal to constant. That means here you can get 2 power n 3 power minus n df, which we can write the 2 power n 3 power minus n df, and this 2 power n we can write 3 power this 2 power n, that n of delta is directional delta power minus df, 3 power n df we will get. This one is 3 power n df. So 3 power n df time 3 power minus n df, so we can get 3 power 0, which is equal to 1. So we know that this df is, the df is ln 2 by ln 3, ln 2 by ln 3. From you can find here, we already obtained this one. If you are applying the box counting method for here, that means 2 power n interval has the relation with 3 power n df. One can apply logarithmic, then df one can get ln of 2 power n over ln of 3 power n. So which we will get ln 2 by ln 3. Now this moment, if we are applying, the moment is similar. Now you can observe that in this moment there is no involvement of n. If n tends to infinity, the moment remain constant. The moment remain constant. That means the total mass equal to 1. The total mass is 1. So this moment is independent of the value of n. The m df moment of this probability or this measure is remain constant, which is independent of n. Now then see that the number of remaining interval have their size finite enough to make their dfth moment equal to the size of the initiator. That means this dfth moment equal to 1. Then what is the initiator? We started with the interval 0, 1. So if you are applying dfth moment, then total mass we are getting as 1, which is equal to the size of the initiator. So then see that the number of remaining intervals have their sizes finite enough to make their dfth moment. If the size of the each interval is make us their dfth moment, if you are taking the sum of all the value, then it is the size of the initiator. On the other hand, how many interval we removed from the closed interval 0, 1 and we obtained the Cantor interval is, in the first the iteration we are removing one interval of length 1 by 3 and 2 interval of length 1 by 9 and 4 interval of length 1 by 3 power 3 and so goes on. You can take 1 by 3, we will get this quantity. This geometric series converges to 1 over 1 minus 2 by 3. If you are solving this, one can get 1, which we already discussed in our first class itself. So the sum of all the interval which are being deleted is, we deleted all the interval, literally 1. It implies that n tends to infinity, there is apparently nothing left in the system, albeit equation A suggests otherwise. This equation A suggests that there is a constant movement that preserves the movement equal to 1. This is the surprising fact in the Cantor set. So with respect to the df, the moment remaining constant. Therefore, this df is the conserved quantity in the triadic Cantor set. This quantity we are calling as the fractal dimension of the set Cantor set. Now we will check, is there any conserved quantity in the Sierpinski triangle. We will use the same argument in the Cantor set. In the Sierpinski triangle, in the construction, I just recalling here, in each iteration we are removing 3 interval of length 1 by 2. That means 3 power n in general, 3 power n interval of size 1 by 2 power n. That means you can divide the side by 2 equal parts and join the midpoints. Remove the interior, not on the boundary. Remove the interior, then one can get this type of structure. Like this type of structure, we are just removing this interior. Now here, after the first iteration, we have 3 interval, each of its size is 1 by 2 power 1. Now apply the same procedure here and here in the east subtriangle. So after the second iteration, we will get this type of triangle. Now this interior is removed. Now here 3 triangle of length 1 by 4. 3 triangle is length 1 by 4. 3 triangle is length 1 by 4. That means 3 power 2 triangle of length 1 by 3, 9, 3 power 2 triangle of length 1 by 2 power 2. So in general, in the nth iteration, we have 3 power n triangle, individually having 3 edges of length 2 power 1 by 2 power n or 2 power minus n. The 3 edges, each of its size is 1 by 2 power n. Therefore, the length of the entire Sierpinski triangle is this one, 3 times 3 power n times 2 power minus n. This approaches to infinity as n tends to infinity. Also, it gives the total length of the Sierpinski triangle is infinity. Moreover, eliminating n from the scaling law. N of delta, that means the number of boxes, minimum number of boxes required to cover the this Sierpinski triangle follows this power law df. Then one can get this df as ln 3 by ln 2. That means 3 power n triangle of 2 power minus n df. So this is 1 by 2 we are getting, therefore it will become plus. So now df is ln 3 by ln 2, that the n will cancel. Now we will give the moment for this each triangle. Suppose x1, x2, xn are size of the each equilateral triangle after the nth iteration. So here n equal to, after the nth iteration, how many number of triangle we have? 3 power n triangle. Each of its size is x1, x2, xn, we are remaining, each of its size is 2 power minus n. The qth moment of the remaining equilateral triangle, that means how many triangle is remaining after removing, their moment is defined as like this one. So here each x1, x2, xi equal to 1 by 2 power n, and total number of triangle is 3 power n. At the nth step, construction process. Now let us try what is the m naught. So m naught equals sum of I equal to 1 to 3 power n triangle, each of its size is 1 by 2 power n power 0, then you will get 3 power n. We will get 3 power n. Whenever this n tends to infinity, this m naught tends to infinity, because this m naught is a decreasing quantity. Now we can find what is m1, first moment on the remaining triangle in the Sierpinski triangle. Summation I equal to 1 to 3 power n 1 by 2 power n power 1. So we'll get 3 power n times 1 by 2 power n. So one can get 3 by 2 power n. So whenever n tends to, maybe if we can write this 3 power n as in term of 2 power n, because we need 3 power n and 2 power minus n, 2 power minus n. So here the number of boxes is required to cover the object is delta power minus df. Here ndf we obtained in the previous slide. Here 3 power n is equal to 2 power n df. Instead of 3 power n, if you are replacing this one, then one can get 3 power n as 2 power n df times 2 power minus n. Therefore, which we get 2 power n as df minus 1 or 2 power minus 1 times n, that means 1 minus df. So which is 1 by 2 power n times 1 minus df. Here understand that the 1 minus df is, df value we are getting as ln 3 by ln 2, which is greater than 1, which is greater than 1. This you are increasing, this also tends to infinity. Also this we can make it from here itself. If n tends to infinity, this quantity also goes to infinity. This quantity also goes to infinity. So because this one will get negative, then again it goes to in the positive power. That means the same it will comes to plus. So it goes to infinity. So if you are applying m1, if you are applying the first moment on the remaining triangle, so we are getting this tends to infinity as n tends to infinity. First moment also tends to infinity as n tends to infinity. Now we will find the, so m0, m1 are increasing quantity with n, whereas m2 is decreasing quantity they are mentioning. Now find what is the m2. If you are taking the m2, then from same we are getting 3 sum of I equal to 1 to 3 power n 1 by 2 power n power 2. So which we will get 3 power n times 2 power minus 2n. Instead of this 3 power n, we can use this quantity. We can use this quantity. So 2 power n df times 2 power minus 2n. If you are taking 2n as common, then one can get df minus 2. 2 power n as common, df minus 2. The df value is given, it is greater than 1, but it is also less than 2. So this we can write as 2 power minus n 2 minus df. Now this value is less than 1, therefore if n tends to infinity, this quantity is goes to 0. This quantity goes to, that means m2 is goes to 0 as n tends to infinity. So one can observe that m1 goes to infinity and m2 goes to m0 goes to infinity and m2 goes to 0 as n tends to infinity. Therefore one can understand that there is a q belongs to 1 to 2 such that qth moment is equal to 1, like a Cantor set. That qth moment we can take ln 3 by ln 2 by using this quantity, then one can show that this one equal to 1, that means 3 power n times 2 power minus n df. Now instead of this 3 power n, you can take 2 power n df and times 2 power minus n df. With respect to this df, we will get 1. That df we are obtained from this relation. The df is 3 by 2. Df is 3 by ln 3 by ln 2. Now, with respect to this df, the qth moment m df is equal to 1. Again, you can observe that which is also independent of the iteration n, and dfth moment equal to the size of the initiator S naught, because S naught we are started from the equilateral triangle with the side length 1. So, 3 triangle of side length 1 we will get finally, which is as 1. So, this dfth moment in each iteration, if you are taking the size of each triangle as this ratio, then you can find the total mass which is equal to the mass of the initiator. Therefore, here also df is a conserved quantity. That means one can show that in the same manner one can show that in the van Koch curve we can find the moment and find that in the dfth moment we can get as 1, where the df we can take as ln 4 by ln 3, one can get df. Similar manner we can, but we are not removing, we are making it the side of the equilateral triangle. So, this df we are calling as the fractal dimension of the object. So, if you are finding the total mass of the object of with respect to this fth moment, which is equal to constant, the density is constant. So, this is the some surprising nature in the fractals, because if you are taking the interval, you can divide the interval as a parts. Maybe you can interval as a parts. Then for example, you can take the 0, 1, divide it to interval, make their union 0, 1 by 2 and 1 by 2, 1, take the union, we will get closed interval 0, 1. That means an object is decomposed into the parts. Then if you want to find the length of the whole, you can find the length of this one and take the union, you will get 1. Therefore, here if you are finding the first moment, it preserves the length. If you are taking the area, of the surface, again you can decompose into the parts, then find the area of each pieces. Then if you want to find the area of whole, find the area of the pieces, then take the union, you will get, that is the second moment is preserves the area. The second moment is constant with respect to any decomposition. If you are going to the volume, the third moment is we are getting the constant. In the fractal, instead of the integer values, the fractional values, the values lies between 1 and 2, 2 and 3. For example, in the Cantor set, we are getting the dfth moment, it lies between 0 and 1. In the Sierpinski triangle, the moment is lies between 1 and 2. This fractional moment, with respect to this fractional moment, their moment is equal to the size of the initiator, it is constant value. Whereas in the regular object, the moment is integers. Here the moment is a fractional value. So, this is how the fractal object are differ from the classical Euclidean objects. Now, we will define the multifractal nature of this object, Triadic Cantor set and Sierpinski triangle, by using the multifractality formalism. In the next class, we will discuss the how to define the multifractality of this triadic Cantor set and Sierpinski triangle by using these moments. Thank you.